When NASA's New Horizons spacecraft flew past Pluto in 2015, it gave us something we never had before, a close-up view of a world that had only been a blurry dot for decades. What it revealed was stunning. This distant dwarf planet once thought to be lifeless and dull turned out to be surprisingly dynamic. For generations, Pluto remained a mystery to scientists and space enthusiasts alike. Located at the far edges of our solar system, this tiny world appeared as nothing more than a faint speck through even the most powerful telescopes on Earth. Many astronomers believed it was simply a frozen, inactive ball of ice drifting through the darkness of space. The journey to discover the truth about Pluto began long before the New Horizons mission launched. Scientists debated for years whether a mission to such a distant object was worth the time and resources. Some argued that Pluto was too small and too far away to justify the expense. Others insisted that exploring the unknown was precisely what made space exploration valuable. After much discussion and planning, NASA finally approved the New Horizons mission in 2001. The spacecraft was designed to travel faster than any previous mission. Yet even at its incredible speed of about 50,000 kilometers per hour, it would take nearly a decade to reach its destination. This timeline alone taught an important lesson about patience and commitment to long-term goals. The spacecraft launched in January 2006, carrying with it the hopes and dreams of scientists who had dedicated their careers to understanding the outer solar system. For 9 years, the team monitored New Horizons as it sped through space, making course corrections and preparing for its brief but crucial flyby of Pluto. As New Horizons approached its target in July 2015, excitement built among the scientific community. The first images sent back to Earth showed more detail than humans had ever seen before. Each new picture revealed Pluto to be more complex and interesting than anyone had imagined. The spacecraft discovered mountains of water ice standing as tall as the Rocky Mountains on Earth. It found vast plains of nitrogen ice that appeared to flow like glaciers across the surface. Most surprisingly, it captured images of a heart-shaped region that quickly became Pluto's most famous feature. This area, later named Tombo Regio after Pluto's discoverer, showed signs of active geology that scientists had thought impossible on such a cold, distant world. Perhaps most unexpected was the atmosphere. Pluto had a thin layer of gases surrounding it, primarily nitrogen with traces of methane and carbon monoxide. This atmosphere created a beautiful blue haze when viewed against the sunlight, similar to the blue skies of Earth, but caused by very different processes. The New Horizons team celebrated these discoveries, but their excitement soon turned to confusion. When they analyzed the temperature data from Pluto's atmosphere, something didn't make sense. According to all their models and calculations, Pluto's upper atmosphere should have been around 100 Kelvin, about -173 Celsius. Instead, the measurements showed temperatures closer to 70 Kelvin, significantly colder than predicted. This temperature difference wasn't a small discrepancy. It represented a fundamental gap in scientific understanding of how planetary atmospheres work. Something was cooling Pluto's atmosphere much more efficiently than any known process could explain. The team checked their instruments, reviewed their calculations, and confirmed the readings were accurate. As scientists puzzled over this mystery, they realized they were facing a question that challenged basic principles of planetary science. Whatever was happening on Pluto might force them to reconsider how atmospheres function throughout the universe. But what could possibly explain such dramatic cooling in the thin air of this distant world? The answer would prove stranger than anyone could have imagined. The mystery of Pluto's unexpectedly cold atmosphere puzzled scientists for years. After the New Horizons flyby, they reviewed the data repeatedly, searching for errors or alternative explanations. Nothing seemed to solve the temperature problem. The atmosphere was simply much colder than any existing scientific model could explain. Scientists began to focus their attention on one particular feature of Pluto: its haze layers. The New Horizons spacecraft had captured beautiful images of these layers, extending high above the dwarf planet's surface. The haze appeared blue when backlit by the sun, creating an ethereal glow around Pluto. But could these delicate layers of particles be more than just a pretty sight? In 2017, a planetary scientist named Xi Zhang from the University of California, Santa Cruz proposed a bold new theory. Zhang suggested that the tiny particles making up Pluto's haze might be actively cooling the entire atmosphere. According to his idea, these particles absorbed sunlight and then radiated that energy away as heat in the infrared spectrum, effectively acting as tiny cooling machines throughout the atmosphere. This concept challenged fundamental assumptions about how planetary atmospheres work. On Earth and other planets in our solar system, gases control most of the heating and cooling processes. The idea that solid particles suspended in the air could dominate temperature regulation was revolutionary. Many scientists were skeptical at first, viewing Zhang's proposal as interesting, but unlikely. Testing this theory proved difficult. Earth-based telescopes lacked the sensitivity to detect the faint infrared signals from Pluto's distant atmosphere. Even the Hubble Space Telescope, powerful as it was, couldn't provide the specific type of infrared observations needed. Scientists needed a new tool, one designed specifically to detect infrared light from distant objects. The James Webb Space Telescope represented humanity's best hope for solving the Pluto mystery. This massive observatory, with its 6.5-meter gold-plated mirror and advanced infrared instruments, was designed to see the universe in ways never before possible. But the telescope faced numerous delays and challenges during its development. Scientists working on the Pluto problem had to wait patiently as Webb's launch date was pushed back multiple times. Finally, in December 2021, the James Webb Space Telescope launched successfully. After months of careful deployment and calibration in space, the telescope was ready to begin its scientific mission. In May 2023, an international team led by researcher Tandai Bertrand pointed Webb's powerful instruments toward Pluto. The telescope's mid-infrared instrument MIRI collected data about the heat being emitted from both Pluto and its largest moon, Charon. For the first time ever, scientists could clearly separate the infrared signals from these two worlds. This capability was crucial, because previous observations had always blended the heat signatures together, making it impossible to study Pluto's atmosphere in isolation. When the research team analyzed Webb's data, they found something remarkable. The infrared emissions from Pluto matched exactly what Zhang had predicted years earlier. The haze particles were indeed radiating heat in the specific infrared wavelengths his theory had suggested. This confirmation transformed a controversial hypothesis into established science. The discovery revealed that Pluto's atmosphere works fundamentally differently from any other known planetary atmosphere. Rather than gases controlling the temperature, the tiny solid particles suspended in the air dominate the energy balance. These particles, formed when ultraviolet light breaks down methane molecules high in the atmosphere, create a cooling effect powerful enough to explain the temperature mystery that had puzzled scientists for nearly a decade. This breakthrough changed how scientists think about planetary atmospheres throughout the universe. But as they celebrated solving one mystery, researchers realized they had stumbled upon an even bigger question. If haze particles could control Pluto's climate so dramatically, what other worlds might be governed by similar processes? And what might this mean for the search for life beyond Earth? The discovery about Pluto's haze changed scientific understanding. Far beyond this single dwarf planet, researchers quickly realized that what they learned from Pluto could apply to many other worlds. Throughout the universe, this small, distant object had suddenly become a key to understanding atmospheric processes everywhere. Scientists began to look at other bodies in our solar system with new eyes. Saturn's moon Titan, with its thick orange haze, became particularly interesting. Researchers had always known that Titan's atmosphere contained complex particles similar to those on Pluto. Now they wondered if these particles might also play a major role in controlling Titan's temperature. The same questions applied to Neptune's moon Triton, which shares many features with Pluto. The implications extended even further to planets orbiting other stars. Astronomers have discovered thousands of exoplanets in recent years, many with atmospheres that might contain haze layers. The traditional models used to predict temperatures on these distant worlds relied primarily on gas behavior. If Pluto taught scientists anything, it was that these models might be missing a crucial factor. Worlds that seemed too cold for liquid water based on gas-only models might actually be warmer if their hazes worked differently than expected. This realization had profound implications for the search for life beyond Earth. Temperature is one of the most important factors determining whether a planet can support life as we know it. If scientists had been calculating temperatures incorrectly by ignoring the effects of atmospheric particles, they might need to reconsider which planets fall within the habitable zone around their stars. The Pluto discovery also connected to Earth's own distant past. Scientists believe that early in our planet's history, before oxygen became abundant, Earth's atmosphere contained haze layers somewhat similar to those on Pluto. These ancient hazes might have played an important role in regulating Earth's climate during the critical period when life was first emerging. By understanding Pluto better, researchers gained new insights into how our own world developed. Beyond the scientific implications, Pluto's story offered valuable lessons about human knowledge and discovery. It reminded scientists to question their assumptions and remain open to surprising answers. The researchers who solved the mystery succeeded because they were willing to consider ideas that initially seemed unlikely or even impossible. Their persistence in pursuing unconventional theories ultimately led to a breakthrough. The journey from observation to explanation also highlighted the importance of technological development. Without the James Webb Space Telescope, the mystery of Pluto's cold atmosphere might have remained unsolved for decades. This powerful new tool allowed scientists to see what was previously invisible, demonstrating how advances in technology often drive scientific progress forward. Perhaps most importantly, Pluto's story showed how exploration of even the most distant and seemingly insignificant objects can yield knowledge with far-reaching implications. When New Horizons was first proposed, many questioned the value of visiting such a small, faraway world. The discoveries that followed proved that every corner of the universe holds potential for expanding human understanding. As scientists continue to analyze data from Pluto and apply these lessons to other worlds, they face new questions that push the boundaries of knowledge even further. Could atmospheric hazes play a role in making some exoplanets habitable? Might similar processes occur in atmospheres composed of different chemicals? And what other fundamental assumptions about planetary science might still need revision? The story of Pluto's mysterious atmosphere reminds us that the universe contains countless secrets waiting to be discovered. Each answer reveals new questions, and each solution opens doors to deeper mysteries. What other revolutionary discoveries might be hiding in plain sight, challenging us to look at familiar objects with fresh perspective and wonder?